So let's take a look at trig substitution. Now, before we get to that, let's set the scene with our most popular style of substitution. That's going to be u substitution. So if we have the square root of 1 plus x dx, if you want to integrate this, you can simply choose u to be equal to 1 plus x dx, and then everything's great. If you have the integral of the square root of 1 plus x squared dx, if you try to say u equal 1 plus x squared, well, you run into some problems here, because what you find is that du is equal to 2x dx. However, you do not have an x dx. That doesn't appear there, so you can't do u substitution here. However, if you have the integral of x times the square root of 1 plus x squared dx, well, here you could successfully choose u to be 1 plus x squared, and then you'll be able to integrate this. So the trig substitution is going to come into play when we're dealing with these types of integrals, where we have a square root that's present, but u substitution will not work for us. So when we think about the issue with square roots is that integrating them obviously is tricky, but they become very simple when you have something like a square root and then something squared. Because since the square root and the squared are essentially inverses of one another, we can eventually cancel these. So if I could be able to replace this thing underneath my square root with something squared, I could get rid of the square root. So what we want to think about now is, what do we have that when you add things together, maybe square things, that you end up with something squared? Well, the favorite formula from back in everyone's trig days is sine squared plus cosine squared is equal to 1. So this formula is going to be driving all of the other formulas that we're going to be needing for this section. So what we have here is we could take a look at some, say, partner integrals here. So if we have the square root of 1 minus x squared dx, if I want 1 minus something squared to eventually become this something squared, I could manipulate this ever so slightly and subtract a sine squared theta from both sides. And so what we see is we have cosine squared theta is equal to 1 minus sine squared theta. So over here, if I was to say, let x equal sine theta, then I would be able to plug that in for here. So I would get an integral of the square root of 1 minus sine squared theta, but we know 1 minus sine squared is nothing more than cosine squared theta. So then, as we said over here, we can cancel the square root with the square, so we have the integral and we have a cosine theta. Now, obviously, we have this dx that we have to work with, so we're going to need to substitute this in using our differentials. So we would get a cosine theta d theta. So this guy sticks around here as a cosine theta d theta, cosine theta d theta, cosine theta d theta. So then obviously we would, in this case, we'd be integrating cosine squared theta d theta. So that's what, if we have something of this form, 1 minus x squared, we could easily do this type of substitution. However, if we had, say, a slightly different integral, and we had, say, the integral of the square root of 1 plus x squared dx, if we look back up here, we never have 1 plus something squared to give us that. So we have to go back to this equation, and we're going to manipulate it. One way to manipulate this is we could divide by sine or cosine squared. So if I divide everything by cosine squared, so over here, if I divide by cosine squared theta, divide this by cosine squared theta, and divide this by cosine squared theta, what we get is, if we have sine squared over cosine squared, that becomes tan squared theta. Cosine squared plus cosine squared, or cosine squared divided by cosine squared is 1. 1 divided by cosine squared is secant squared. So now this expression looks a lot like this. So this leads to my choice of my substitution to say, let x be equal to tangent of theta. Then my dx would be secant squared theta d theta. So now when I substitute this in, I'm going to have a square root of 1 plus tangent squared theta, and then I'm going to have a secant squared theta d theta, but then this we know is just equal to secant squared theta, but now I take the square root of that, square root of the squared, this cancels, so I have a secant theta times secant squared theta d theta. Now, the last one that we should be aware of is if we have the integral of a square root and we have, say, x squared minus 1. Now, up here, we had 1 minus x squared. So, unfortunately, we can't do the same thing and just say, oh, what if there's a negative? Because obviously you'll have a negative underneath the square root, and that's an issue. So instead, we're going to take this formula here, and we're just going to subtract 1 from both sides. So I have tan squared theta is equal to a secant squared theta minus 1. And so this formula is going to help us deal with this guy. So what I'm going to choose is I'm going to choose x is equal to a secant theta. So then dx is going to be a tangent theta secant theta d theta. And so when I plug this in underneath here, I'm going to get a square root of secant squared theta minus 1. And then I'm going to have a tan theta secant theta d theta. But this, the important part, is that we get rid of the square root by seeing that this is the same thing as tan squared theta. So now I have the integral of tangent of theta times tangent of theta secant theta d theta. So this is the very basic foundational idea behind your trig substitution, is you're going to have these three formulas. Your cosine squared is equal to 1 minus sine squared, tan squared plus 1 is equal to this and this. And they all are derived from the Pythagorean identity for trig functions. Just as a side note here, you could have subtracted off cosine squared from both sides, and you could get sine squared theta is equal to 1 minus cosine squared theta. So you might have seen this choice of substitution. It doesn't matter, you get the same thing. Sines and cosines are very nice when it comes to integrating them. Now, the next trick that we have to look at is what if we had something like, say, 9 plus x squared dx? Well, what we notice up here is that when it was 1 plus x squared, we chose our x to be tangent, so we could have a secant squared. But we obviously don't want this to be a 9 plus secant squared. We want to be able to factor out a 9, and we're going to be left with a 1 plus something here squared, which ideally will be our secant. So what this means is we have to figure out, how do I factor out a 9 out of both of these? Well, this needs to introduce some type of 9 here in some way. So if I let x be equal to 3 tangent of theta, then my coefficient in front over here is going to become a 9 when it gets squared. So this is going to be my choice. When I plug in, we see that I would have a square root of a 9 plus a 3 tangent theta squared, which becomes obviously 9 plus 9 tan squared theta, which then becomes a 9 times 1 plus tan squared theta, which gives me what I want of 9 secant squared theta, and we said that we always want to have the square root cancel with a squared, and we're going to have a 3 secant theta that's left. So if you have a coefficient, some type of non-1 in the front, you want to be able to just pick this coefficient to be able to factor that out of both of those. So on the one that you had sent me of this integral of a square root of, say, a 49 plus 3x squared dx, or maybe it was a 9, I don't remember now. Maybe, yeah, I'll say this was a 9, I think. Nonetheless, our goal here is going to try to be able to make this number in front. We'd like to have this become a 49 when we do our substitution, so we could factor the 49 out of both of these. So when we pick our x to be something, I want the end result to be 49, so when I square this thing inside here, if I put a 7 over 3, and then I do tangent theta, Notice what I'm going to get is I'm going to get x squared is equal to a 49 over 9 tan squared theta. So then when I plug this in over here, I would have the square root of 49 plus 49 tan squared theta. And then obviously all of this you still have to deal with the dx and stuff. But the important part is understanding this step of being able to simplify this thing underneath the square root. And so you'll have a 49 times 1 plus tan squared theta. And then you can do your substitution that this is secant squared theta. So this is basically all of the ideas behind the initial choice of choosing this substitution. Now, at this point, if that's all you really had questions on, great. I've hopefully been able to answer them for you. Obviously, the last tricky part of these is going to be the very last step. So if you have this integral of something here, say dx, and you do some trig substitution. So let's say we go back up to this guy and we say let x be equal to 7 over 3 tangent theta. Okay, then when we finish our integral, let's say our final answer becomes something like a theta plus a sine theta plus c. Okay. Hypothetically speaking, let's say this is our situation. Now, normally when we do something like u substitution, so if we had, say, a square root of, say, 1 plus x dx, we do u substitution where u is a 1 plus x, and all of this, what we end up getting is some type of result that maybe we'll have a u minus a u squared divided by 2, say, plus c. Substituting back in for the original variable x is very easy. You just simply put this in. The issue here is that when we're trying to go back to the original variable x, I don't have a nice, easy way of saying what is theta in terms of x. Now, in this case, one of these is easier than the other, because what I could multiply or be able to get theta by itself, I could multiply both sides by the reciprocal of this, so I'll have 3/7 x is equal to tangent of theta, and then I could do tan inverse to both sides. So tan inverse, and so what I see is theta is equal to tan inverse of 3x over 7. So I can substitute this in for theta, and I'm going to be back to my original variable x. But sine theta is not that easy, and so I did see when you sent me your solution, you had a really nice picture. That's exactly the idea that we want to use, is knowing that, for instance, a tangent of theta, we know this is obviously opposite over adjacent, so we're going to draw some type of triangle, where if we said that tangent of theta is equal to 3x over 7, what that means is that the opposite side is going to be 3x, the adjacent side is going to be 7. So if my angle here is theta, my opposite is 3x, my adjacent is going to be 7. I now have to solve for this using the Pythagorean theorem, so this is going to be the square root of 9x squared plus 49. So now if I want to be able to figure out what is sine theta, well then I just use obviously what you know about trig. You do opposite over hypotenuse, and so in this case, hypothetically, this is my answer. My answer would be tan inverse of 3x divided by 7 plus 3x divided by the square root of 9x squared plus 49 plus c. So those are the two major steps when it comes to trig substitution. Now, as a note, this is not what you get as the integral of this, so don't be trying to check your answer with that. But just to help you see the two different styles of trying to do back substitution in for the original variable x. And if you had to do other steps, let's say there was a u that had to be thrown in there, just make sure you follow all of the substitutions correctly to get back to the original variable, usually x. So hopefully that helps clarify trig substitution for you. If you do have any other questions, please let me know.